A proof by infinite descent is a particular kind of proof by contradiction. If a solution in natural numbers existed, it would necessarily imply a smaller solution, which in turn would imply an even smaller one, and so on, leading to an infinite descent. But there cannot be an endless change of ever smaller natural numbers, so the original premise that any solution exists must be false. This method was developed and popularized by Pierre de Fermat, though arguments of this type have been known for millennia. A famous early example is the ancient proof that the square root of 2 is irrational. Euclid's proof uses contradiction through division and parity, but it can be easily reformulated as an infinite descent argument. Suppose the square root of 2 can be written as a fraction, where n and k are positive integers. Then we have 2 times k squared equals n squared, so 2 must divide n. Let n equal 2 times n sub 1. Substituting back gives 2 times k squared equals 4 times the square of n sub 1. Thus, 2 times n sub 1 squared equals k squared, which shows that 2 must also divide k. Now we are in the same situation as before, but with a smaller supposed solution. Repeating this process yields a descent with smaller numerators and denominators. But natural numbers cannot shrink indefinitely. Eventually, we would reach 0. Therefore, the original assumption is impossible, and the square root of 2 cannot be rational. The reasoning applied to the rationality of the square root of 2 can be extended to a slightly harder problem, proving that a sum of 2 squares equals 3 times another square has no solution in integers. Any integer can be written as 3 times a quotient plus a residue, with the residue being smaller than the absolute value of 1. See, for example, 5, 6, and 7, whose residues are -1, 0, and +1. Substituting them above gives this expression. When expanding and regrouping, that yields in the left-hand side 3 terms, where the first 2 are divisible by 3. From this, we see that if 3 divides a squared plus b squared, it must also divide the smaller sum r sub 1 squared plus r sub 2 squared. But since r sub 1, r sub 2 can only be -1, 0, or +1, the only way 3 divides this sum of 2 squares is if both r sub 1 and r sub 2 are 0. The following steps mirror the process used in proving the irrationality of the square root of 2. Since r sub 1, r sub 2 equals 0, the equation becomes 9 times k sub 1 squared plus k sub 2 squared, showing that 3 must also divide c. Let c equal 3 times c sub 1. Substituting back, dividing yields k sub 1 squared plus k sub 2 squared equals 3 times c sub 1 squared, which is the same type of equation we started with, but for smaller integers, since k sub 1 squared and k sub 2 squared is smaller than a squared plus b squared. Repeating this process indefinitely leads to an infinite descent, proving that no integer solution exists. Leonardo Bonacci, better known as Fibonacci, stated and sketched an incomplete proof that the sum and differences of 2 squares cannot both be perfect squares. About 4 centuries later, around 1640, Pierre de Fermat gave a complete proof that the area of a right triangle with integer sides is never a square, which is equivalent to showing that the difference of fourth powers cannot be a square. This proof is historically significant because it marks the first detailed use of Fermat's method of infinite descent, the technique he pioneered. He also stated as well that the sum of 2 fourth powers cannot be a square. In 1747, Leonhard Euler extended this line of results by proving that the sum of 2 fourth powers is never a square, applying Fermat's infinite descent method. Since Euler's argument is the most straightforward to follow, we will begin with it. Euler begins by assuming a solution with x, y, and z relatively prime integers. Otherwise, dividing by the common divisor would yield a smaller solution. Moreover, x and y cannot be both odd, for then z would be even, and expanding the terms leads to the absurd conclusion that 4 would divide 2. Thus, x and y must have opposite parity. Without loss of generality, take x odd and y even. Rewriting, we see this is just a Pythagorean equation. The primitive Pythagorean triples formula is this one, where a and b are co-prime of opposite parity. Hence, a squared minus b squared equals x squared, and 2 times a times b equals y squared. Now observe that a squared equals b squared plus x squared is another Pythagorean relation. Since x is odd, b must be even, so a is odd. Thus, a times 2b equals a square. Since a and b are relatively prime, a and 2b must themselves be squares. Now, the Pythagorean parametrization of a squared equals b squared plus x squared is this one, with p and q co-prime of opposite parity. Because a equals a sub 1 squared, this means p squared plus q squared equals a sub 1 squared. Meanwhile, from 2b equals b sub 1 squared, we deduce b sub 1 squared equals p times q. As p and q are co-prime, each must itself be a square. Substituting, we obtain that the sum of p sub 1 raised to the fourth power plus q sub 1 raised to the fourth power equals a square. Thus, we have produced a new solution of the same kind with smaller numbers, since this sum of fourth powers is smaller than the original one. Since this descent can be iterated indefinitely, so no minimal solution can exist other than the trivial ones. Fermat stated the problem as the area of a right triangle cannot be a square. Starting with the Pythagorean equation, primitive solutions are given by this formula, with a and b co-prime and of opposite parity. The area is then a times b times a squared minus b squared. For this to be a square, a, b, and a squared minus b squared must all be squares. This means a equals x squared and b equals y squared, giving x raised to the fourth power minus y raised to the fourth equals a square. Note that while Euler dealt with a sum of fourth powers equals to a square, Fermat treated a difference of fourth powers equals to a square. Factoring, this difference of fourth powers equals a difference of two squares times a sum of two squares. Any common factor of them would divide the sum, which equals 2 times x squared. Since a and b are co-prime of opposite parity, then x and y inherit these properties. So each bracket is a square. Let the sum of squares be equal to m squared and the difference of squares be n squared, with m and n odd. Next, define p as m plus n over 2 and q as m minus n over 2. A common factor of p and q would divide then m, n, x, and y. Hence, p and q are co-prime. Then the area of this smaller triangle is a square, forcing one of p and q to be a square and the other twice a square. The crucial step is noting that p squared plus q squared equals a square too. So we obtain another Pythagorean equation. Its primitive solution has p equals c squared minus d squared and q equals 2 times c times d, with the area of this smaller triangle again a square. Since c and d are co-prime, both must be squares. Say c equals r squared and d equals s squared, yielding the smaller solution r raised to the fourth power minus s raised to the fourth power equals t squared. Thus, an infinite descent arises, so the area of a right triangle can never be a perfect square. Fermat stated that no triangular number greater than 1 is a fourth power. Legendre gave the first published proof. Although his text is not available online, it can be easily reconstructed. Starting with a triangular number equals y raised to the fourth power, we can state it as x times x minus 1 equals 2 times y raised to the fourth. Since x and x minus 1 are consecutive integers, they are co-prime and of opposite parity. One is a fourth power and the other twice a fourth power. Case 1. Assume x equals a raised to the fourth power and x minus 1 equals 2 times b raised to the fourth power, with a odd. the difference is equal to -1. Rearranging and squaring yields these two squares, which can be transformed as the square of a raised to the fourth power plus 1 minus 4 times a raised to the fourth power, which equals 4 times b raised to the eighth power. Dividing through by 4, we obtain a raised to the fourth power plus b squared raised to the fourth power equals the square of a raised to the fourth power plus 1 over 2. Here b must be even, otherwise, since a is odd, a squared plus 1 over 2 is not an integer. This reduces the problem to the sum of fourth powers equals a square, which Euler proved through infinite descent. Case 2. Assume x equals 2 times a raised to the fourth power and x minus 1 equals b raised to the fourth power, with b odd. Following the steps of the previous case, we arrive at a squared raised to the fourth power minus b raised to the fourth power equal the square of b raised to the fourth power minus 1 over 2. This reduces the problem to a differences of fourth power equal a square, which Fermat proved via infinite descent. In 1657, Pierre de Fermat posed the problem of finding a cube which, added to its proper divisors, gives a square. He asserted that the only solutions are 1 and 7 cubed. In modern notation, this amounts to solving 1 plus x squared plus x cubed equals a square, with these two known solutions. In 1658, John Wallis and Bernard Fournicle-Debussy were the first to offer solutions, although only for composite numbers. In 1877, Gerono proved that the only prime number solution is 7. His argument, although elementary, is somewhat lengthy since it requires careful analysis of several cases. Later, the problem was tackled within the broader framework of elliptic curves, where the same result follows more easily. In 1977, Harold Edwards, in his Fermat's Last Theorem, a genetic introduction to algebraic number theorem, presented a proof by infinite descent for the prime case as a guided exercise. This focus seems to reflect Fermat's original aim, to introduce his newly developed method to the mathematical community. Edward begins by factoring the equation as x plus 1 times x squared plus 1. So necessarily x is equal or bigger than minus 1. Since x squared plus 1 cannot be a square unless x equals 0, then these two factors are not coprime. But comparing their sum and difference shows they can only share 2 as a factor. Hence, x plus 1 equals 2 times a square, and x squared plus 1 also equals 2 times a square. Combining these yields the Pythagorean equation, the square of u squared minus 1 plus u raised to the fourth power equals v squared, except when u equals 1. Suggestively, for u equals 2, then x equals 7, yields the smallest Pythagorean triple. Case 1. If x is bigger than 1 and u is odd, then u squared minus 1 equals 2 times p times q. U squared equals p squared minus q squared, and v equals p squared plus q squared, with p and q coprime of opposite parity. Then p minus q and p plus q are odd squared. Set p minus q equals m squared with m odd. Combining u squared minus 1 and u squared yields the square of p minus q minus 2 times q squared equals 1. Thus, 2 times q squared equals m raised to the fourth power minus 1. Squaring both sides and dividing by 4, we obtain q raised to the fourth power plus m raised to the fourth power equals the square of m raised to the fourth power plus 1 over 2. This reduces the problem to a sum of 2 fourth powers equals a square, which Euler proved impossible via infinite descent. Edwards instead cleverly posed that the square of q squared plus 1 minus q raised to the fourth power equals 2 times q squared plus 1, which equals m raised to the fourth power, thus reaching similarly q raised to the fourth power plus m raised to the fourth power equals the square of q squared plus 1. Case 2. If u is even, then u squared minus 1 equals p squared minus q squared, u squared equals 2 times p times q, and v equals p squared plus q squared, with p and q co-prime of opposite parity. Since u squared minus 1 plus v equals 2 times p squared, and v is odd, p must be even. Set p equals 2 times n squared. Combining u squared minus 1 and u squared yields the square of p plus q minus 2 times p squared equals 1. Substituting for p, then 8 times n raised to the fourth power equals the square of p plus q minus 1. Let a equals p plus q minus 1 over 2. Then 2 times n raised to the fourth power equals a times a plus 1. So one of the consecutive integers is a fourth power and the other twice a fourth power. Subcase 1. If a plus 1 equals b raised to the fourth power and a equals 2 times c raised to the fourth power, then b raised to the fourth power equals 2 times c raised to the fourth power plus 1. Edward's trick yields the square of c raised to the fourth power plus 1 minus c raised to the eighth power equals 2 times c raised to the fourth power plus 1, which equals b raised to the fourth power. That is, a sum of two fourth powers equals a square, which Euler proved impossible via infinite descent. Subcase 2. If a plus 1 equals 2 times b raised to the fourth power and a equals c raised to the fourth power, then 2 times b raised to the fourth power equals c raised to the fourth power plus 1. Edward's trick gives the square of b raised to the fourth power minus 1 minus b raised to the eighth power, which equals minus 2 times b raised to the fourth power minus 1, that is, minus c raised to the fourth power. That is, we have a difference of fourth powers equals a square, which Fermat proved impossible via infinite descent for non-trivial solutions. The trivial solution b equals c equal 1 gives a plus 1 equals 2, which equals p plus q plus 1 over 2. Hence, p plus q equals 3. Then we got 8 times n raised to the fourth power equals 3 squared minus 1. So that gives n equals 1, giving p equal 2 and q equal 1. From u squared equal 2 times 2 times 1, we get u equals 2. Finally, x plus 1 equals 8, hence x equals 7, which gives the solution that Fermat gave. In 2025, Frederick II, Holy Roman Emperor, posed the congruent problem, finding the common difference of three squares in arithmetic progression. The first non-trivial example is 1, 5 squared, 7 squared, since 5 squared minus 1 equals 7 squared minus 5 squared, which equals 24. Fibonacci solved the problem by finding a parametric family of solutions. A equals p squared minus 2 times p times q minus q squared, b equals p squared plus q squared, and c equals p squared plus 2 times p times q minus q squared. Then the congruent is 4 times p times q times p squared minus q squared. The solutions a, b, c are naturally related to Pythagorean triples x, y, z, where x equals c plus a over 2, y equals c minus a over 2, and z equals b. Fibonacci also conjectured that the congruent can never be a perfect square, but his proof was incomplete. Around 1640, Fermat gave a complete proof showing that the area of a right triangle with integer sides is never a square. Earlier, in 1636, he had challenged St. Croix the equivalent problem of finding three squares in arithmetic progression whose common difference is itself a square. In 1640, Fermat asserted that no four squares lie in arithmetic progression. A posthumous work of Euler's, published in 1780, contained results whose corollary implied a proof by infinite descent. In 1911, Leonard supplied the first explicit infinite descent proof, though it's not available online. In 2000, Tamas Erdoji proposed an infinite descent argument. In 2007, Alfred van der Poorten published an infinite descent proof which we'll examine next. It demands some unpacking to be followed comfortably. Van der Poorten begins by noting that if there were 4 squares in arithmetic progression, then A, B, C, and D must all be odd and pairwise co-prime. Otherwise, there would be a common factor yielding a smaller solution. Since we're dealing with differences of odd squares, it follows that 4 divides m. By setting m equals 4 times m sub 1, the product becomes the square of ABCD equals a squared times a squared plus 4m sub 1 times a squared plus 8m sub 1 times 8 squared plus 12m sub 1. Van der Poorten's clever step is to create a symmetry by defining 4k m sub 1 as 4k minus 6 times n, 4k 0, 1, 2, and 3. Thus, ABCD squared expands as the product of a squared minus 6n, a squared minus 2n, a squared plus 2n, and a squared plus 6n. We can regroup these terms as a squared minus 4n squared times a squared minus 6n squared. And that in turn simplifies neatly to the square of a squared minus 20n squared minus 4n to the 4th power. This yields a Pythagorean equation with parametrization. ABCD equals u squared minus b squared, the square of 4n equals 2 times u times v, and a squared minus 20n squared equals u squared plus b squared. Since ABCD and a squared minus 20n squared are co-prime and their sum equals 2 times u squared, they cannot share a factor of u, nor 2. Otherwise, 4 would divide ABCD, which is odd. Therefore, u and v are co-prime of opposite parity. Case 1. Let v be odd, then u equals 2 times w. Then the square of 4n equals 4 times w times v, implying 4 times n squared equals w times v. This forces w to be 4 times a square and v also be a square. Substituting a squared minus 20n squared equals a squared minus 5 times w times v, which equals 4 times w squared plus v squared. Finally, regrouping and substituting, we got 2 factors. The first is 16 times w sub 1 squared plus v sub 1 squared, and the other one is 4 times w sub 1 squared plus v sub 1 squared. The product equals a squared. These 2 factors are both odd and co-prime, since any common factor would also divide their difference 12 times w sub 1 squared. Such divisor cannot be 4, as the factors are odd, nor w sub 1, co-prime by construction, nor 3. An odd power of 3 cannot be expressed as a sum of 2 squares. Therefore, each factor is a square. Case 2. Let u be odd, then v equals 2 times z. A similar argument yields u sub 2 squared plus 16 times z sub 2 squared equals a square, and u sub 2 squared plus 4 times z sub 2 squared equals another square. Because cases 1 and 2 are symmetric, we only need to analyze one in detail. These 2 equalities are Pythagorean, with their proper parametrization. The first one, 4w sub 1 equals 2 times 2x sub 1 times y sub 1. v sub 1 equals 4x sub 1 squared minus y sub 1 squared, and a sub 1 equals 4x sub 1 squared plus y sub 1 squared. The second equation has parametrization 2w sub 1 equals 2x sub 2 y sub 2, v sub 1 equals x sub 2 squared minus y sub 2 squared, and a sub 2 equals x sub 2 squared plus y sub 2 squared, with x sub I and y sub I co-prime of opposite parity. From w sub 1, it follows that x sub 1, y sub 1 equals x sub 2, y sub 2, while from v sub 1, we deduce that 4x sub 1 squared plus y sub 2 squared equals x sub 2 squared plus y sub 1 squared. So we need to sort out x sub 1 times y sub 1 equals x sub 2 times y sub 2. If x sub 1 equals x sub 2, then y sub 1 equals y sub 2. Substituting yields 4x sub 1 squared plus y sub 1 squared equals x sub 1 squared plus y sub 1 squared. Thus, 3x sub 1 squared equals 0, forcing w sub 1 to be 0. Hence, n equals 0, leading to a trivial arithmetic progression a equal b equals c equal d. If instead x sub 1 equals y sub 2, then y sub 1 equals x sub 2. Substituting yields 5x sub 1 squared equals 2y sub 1 squared, which is impossible by the infinite descent reasoning used before to prove the irrationality of the square root of 2, unless x sub 1 equals x sub 2 equals y sub 1 equals y sub 2 equals 0. Then n equals 0, thus the trivial arithmetic progression a equal b equals c equal d equals 0. Therefore, some prime factors of x sub 1 divide x sub 2 or y sub 2, and similarly for prime factors of y sub 1. Before proceeding with fixed parities, notice that for v sub 1 to be odd, then y sub 1 must also be odd, then x sub 1 is even. Since 4 divides y sub 1 squared minus 1, then it divides v sub 1 plus 1, which equals 4 times x sub 1 squared minus y sub 1 squared minus 1. And so also divides x sub 2 squared minus y sub 2 squared plus 1. Given that x sub 2 and y sub 2 have opposite parity, if y sub 2 is even, then 4 should divide x sub 2 squared plus 1. But it's only divisible by 2, so this option is ruled out. If instead y sub 2 is odd, then 4 divides both x sub 2 squared and y sub 2 squared minus 1. Thus, we fixed parities. X sub 1 and x sub 2 are even, while y sub 1 and y sub 2 are odd. Now we define x sub 1 equals 2 times a times c, y sub 1 equals b times d, x sub 2 equals 2 times a times b, and y sub 2 equals c times d, with a, b, c, d pairwise co-prime. Substituting yields this expression. After factoring out c squared and d squared, we get c squared times 16a squared plus d squared equals b squared times 4a squared plus d squared. Given that b and c are co-prime, then both 16a squared plus d squared and 4a squared plus d squared are perfect squares. This reproduces the same structure as the original arithmetic progression, with first square a squared minus 6n and differences for n. With the product of these two factors being a square, we can infer another arithmetic progression of 4 squares with difference for AD. Since AD divides W sub 1 and hence divides n, this yields a smaller primitive solution completing the infinite descent. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Your support means a lot.